A mole is 6.02 times 10 to the 23rd representative particles, and that number, the number of particles in a mole, is often referred to as Avogadro's number. So what I want to look at in this video is kind of how that number came about historically and how it is experimentally determined. So there are a handful of fairly important bodies in this process, but one, of course, that the number is named after, Amedeo Avogadro. And you can look at the dates there, late 17, early 1800s. And Avogadro did not, in fact, determine the number 6.02 times 10 to the 23rd. He just proposed kind of a theoretical framework that allowed the idea of counting particles to be a viable experimental process. And Avogadro's hypothesis were that equal volumes of gas contain equal number of particles, provided that they're the same temperature and pressure. And it relied on a developing theoretical framework around that time called the kinetic theory of gases. The kinetic theory of gases simply states that all matter is composed of tiny particles in constant random motion. And what we can do then is we can think about what are the implications of a bunch of particles, say in this box, moving around in random motion inside that box. And there are a handful of measurements that we can take, what are referred to as macroscopic measurements, things that we can measure at our level that can allow us to make some inferences about what's going on with the individual particles. And of course, if these particles are atoms, then the particles are going to be too small for us to ever measure, and there are way too many of them for us to ever actually count. And so thinking about some of those properties that we might be able to measure, one of them is volume. And with respect to the kinetic theory of gases, volume is just how much space do the particles have to move about in. The next thing we would look at is pressure. And pressure in a contained gas is the result of gas particles colliding with the surface of the container. Pressure is force over area. Our little cube here has an internal surface area, and the force exerted on that surface area is how many collisions and how hard are the collisions with that container in any given unit of time. And then the last one is temperature. The thermodynamic definition of temperature, or the kinetic theory definition of temperature, is going to be the average kinetic energy of particles in a sample of matter. It's how fast are the particles moving. Faster they're moving, the higher the temperature. Again, it's an average, and we can use temperature as an inference to that average, but it's not confirmable. And so you have to rely on some experimental data that suggests that if we double the temperature, then we're doubling the speed of the particles. And so how does Avogadro's hypothesis work? Well, he said equal volumes of gas in the same container at the same temperature and pressure have the same number of particles. So equal volumes of gas. So let's say we've got 2 cubes here. So we have the same amount of space to move around in. If they're at the same temperature, then all the particles are moving at the same speed. And if they're at the same pressure, then you have the same number of collisions. You can't count those particles, but if volume, pressure, and temperature are the same in 2 containers, then you have to have the same number of particles. Because if you have the particles moving at the same speed in the same size container, and you double the number of particles, you're going to have way more collisions, and your pressure is going to go up. So the only way to keep pressure constant under that situation in both containers is to have the same number of particles. So what Avogadro's hypothesis and the kinetic theory allows us to do is it allows us to use things like temperature, which I can measure with a thermometer, or pressure, which I can measure with a pressure gauge, or volume, which I can measure by measuring the length, width, and thickness of that box, and use those macroscopic measurements to infer what's going on with the particles inside and to indirectly count them, or at least to say this box A and this box B have the same number of particles. A little bit later in the 1800s, a guy by the name of Joseph Lockschmidt used this kinetic theory to predict how many particles would have to be in a cubic centimeter of gas, how many particles of essentially air, so nitrogen and oxygen primarily. He was able to use pressure and temperature measurements to actually come up with a number of particles, which would later lead us to sort out the number of particles in a mole. And that leads us to Robert Milliken. Robert Milliken measured the charge of a mole of electrons in what is famously known as the Milliken Experiment, which is really a pretty fascinating experimental setup. So it looks a little bit like this. You hook up two charge plates to some kind of a power source. So if you look in the top left corner, that's the actual apparatus that was used, and you can see down in our picture here that this is kind of a mock-up of what's going on there. So in the top of this chamber, you're gonna inject a mist of oil. When that oil hits that positive charge plate, it's going to charge. It's going to have an effect of charging those oil droplets negatively. And so any oil droplets that fall through that tiny hole are going to then enter this middle chamber between the two plates. And if the bottom plate is negatively charged, we can figure out the charged force that's pushing up on that force, and it has a gravitational force, a weight, pulling it down. And when you can get the current in that charged plate to be just so that it pushes up with the exact amount of force that gravity pulls down, you can actually get the oil droplet to suspend in between those two plates. And we know that it's suspended because you have a microscope lens set up there, and you can actually look inside the container and see the suspended oil droplet. Well, we can measure the mass of the oil droplet, and we can measure the charge force. We also know what the charge on a single electron is, because we sorted that out with the Thomson experiment when the electron was discovered. And so what he was able to do with a little bit of math is sort out what would be the mass of a mole of electrons. And from there, you can begin to sort out how many particles would have to be in a mole of electrons in the charge to mass ratio. And so that would give you an estimation of the particles in a mole. And you get pretty darn close to 6.02 times 10 to the 23rd. A slightly more modern version of this would be to use what's called X-ray crystallography. And in X-ray crystallography, you're going to shoot X-rays at the solid form of really any substance. It doesn't have to be a diamond. That's just for the image there. So if you put something in its solid form, that's kind of how we refer to it is in its crystalline structure, and you shoot a bunch of X-rays at it. X-rays are going to go right through electron clouds, but they're going to scatter around nuclei. And so you can look at the scatter patterns. They're going to hit a photographic plate there, and you can figure out how many atoms are in a particular cross-sectional area. And so that allows you, again, to count the number of atoms in a very small portion of the sample. You can extrapolate that out to the full cross-section of your sample and predict how many atoms are in whatever mass of sample you put into the machine. And that allows you to really accurately predict how many particles are in that sample. And so when you run this through really just about any substance, you get 6.0214179930 times 10 to the 23rd, or at least with one version of this experiment, which I recorded back in 2014 is when I would have done that. You can actually see that number written out in its complete form, not in the scientific notation. Notice where the estimation is. So we know how many particles are in a mole, give or take, 10 to the 14th? That's a lot of uncertainty, but 10 to the 14th atoms doesn't weigh 4 decimal places on a gram scale, so you wouldn't notice whether you had more or fewer of those. And so there's a kind of an averaging of a bunch of data sets of radiocrystallography that'll tell us how many particles are in a mole. You can see how that data was reported in 2014. In 2019, it was determined that the mole was going to be re-standardized to be a fixed number of particles. Rather than fixing the gram and back calculating how many particles in a mole, we would fix the number of particles in a mole and use that to standardize a gram. And that happened when measurement was kind of re-standardized in 2019, and the mole was standardized to 6.02214076 times 10 to the 23rd to be an exact number. the same way that when we say a dozen, we mean exactly 12. Everyone always likes to throw out the baker's dozen is 13, but a baker's dozen is a completely different thing than a dozen. A dozen means 12 no matter what you're counting. A mole means 6.02214,076 times 10 to the 23rd, no matter what you're counting. We are going to round that number off to just 6.02 times 10 to the 23rd because it's as close as we need to get for the math that we're doing. And that's how you know how many particles are in a mole.